Okay, so hello everyone. So we are going to have our today's lesson very soon. Okay. So and actually today is the last part. So we need to cover. So in this separation science. So and today we're going to focus on the capillary electrophoresis. Okay. So and next week everybody should know that it's the oral presentation day. So you have to really prepare for the group oral presentation. And one thing I really want to remind you guys is it's better for you guys to have rehearsal. So online, so for the whole group first, before you do this oral presentation so in class. So try to arrange a time so for the group rehearsal, and then so because I know like you guys like maybe separate your workload, right? So maybe one prepared for the introduction part, the other prepare for the second part, and so on. So just make sure so you guys like just put everything together, and your like PowerPoints looks like uniform and looks nice. And then so it's better like you do rehearsal and each group member get involved and then to do presentation, and then you have a good time management, because we are going to be very strict on the time. So when time is up, so I would just ask to stop. Okay. So because we have to finish all the groups so next Wednesday. So that's why. So we have to be very strict on the time control. So and for that part, it's better to practice before you really do the oral presentation. Okay. So and now we're soon going to start. We're going to talk about capillary electrophoresis today. Okay. So for capillary electrophoresis, I actually mentioned a little bit already, right? So you see, I have something wrong with my PowerPoint. Okay, finally works. Okay, for capillary electrophoresis, we already mentioned that it's a relatively new technique and often used for a high efficient separation of the sample ions. So we say high efficiency, later on you will see that. So we compare that N number so with the normal HPLC, and we will see that. And also we see that the difference of that one of the normal HPLC is kind of the LC technique, but it's like say a new version, level one. One thing we see is like it uses capillary tube, you see? So it's capillary tube, like something similar to the GC column. It's the fused silica one, that's very common one. And the ID is about 25 to 75 micrometer. So, and also this tube is relatively short, okay? It's relatively short. It's like say, normally it's less than 100 centimeter, can be 50 centimeter or 60 centimeter. So it's relatively short capillary tube. And also another thing you can say is there's no pump. So the driving force is all applied by the high voltage power supply. And this high voltage power supply apply the electrical field on two electrodes. One is cathode and the other is anode. Okay. So and cathode anode, they're put in the two buffer reservoir, okay, and then so the inlet side is called the source vial, and the side that close to the detector of the tube is called the destination vial, okay, and then so they are filled with the buffer solution. The buffer solution, so they are those conductive medium, okay, so which is normally aqueous buffer in most of the cases. And then to introduce the sample, we say that then you can just put the inlet into the sample vial. And in many cases, and then the electrode go together into vial as well. And then so we mentioned that there are different ways to apply the sample. So you can either the voltage or pressure or something like vacuum and so on to apply the sample for a period of time. And then you put it back into this like source vial. And then when the voltage, when this high electric field applies, okay, normally the electric field, the voltage can be how much? The voltage can be like 30 k volts or like 40 k volts, can up to 40 k volts. It can be very high, okay? Apply that electric field, and then so the migration of those ions, not just ions, actually, even including neutral compound starts, right? I say the migration starts, and the driving force is the electrical field, which is supplied by the high voltage power supply. Okay, so And how they could separate it? Remember last time I mentioned about two terms that is very important for capillary electrophoresis. I say all the ions, don't matter it's negative charged or positively charged or even neutral compound without any charge under normal condition, okay? So common conditions say they all migrate to this side. They all migrate to the destination mark. They all migrate to the cathode under normal condition, okay? So, and this is due to the movement of the bulk buffer solution movement, and this is called electro-osmotic flow. So we'll see that again. It's electro-osmotic flow. And then so, however, then if everything goes there, then how could they separate? And then the separation is happen due to the charge. They have different charge, positive or negative. And also the charge density is something we can mention about that cause about the separation. It is a little bit similar to what we talk about in IC, but still, so the elution order may be different. So it's different. It's in IC every time you can just either to do cation separation or ionized separation. But here in capillary electrophoresis, you can do the cation separation and ionized separation in one single run. You can do that simultaneously, okay? So this is one, the key is different. And then so, and the separation is based on, you see, so electrophoretic mobility. Now we're going to look at these two, the EOF and EP. So you can see. So EOF. So what is EOF? Electro-osmotic flow. Okay. So, and what is EP? Electrophoretic mobility. We call that electrophoretic mobility. This is the one that causes the separation. Separation is achieved because different ions, they have different electrophoretic mobility. What is that? So it is the response of the ions to electrical field. As already see that, we say that this one's cathode and this is anode, right? Okay, so this is cathode and this is the anode. So here is the cathode. Okay, so here is anode. Okay, so the cathode, the anode. So that in that one, and tube, this one. So okay, and this is the detector. So detector. This end. Sorry. Okay, so and what happened is like if it's cathode and anode, and then so which ion is attracted toward cathode? Cations, right? So the cations will be attracted to this end, they have attraction, pull it to the cathode. And then how about the ionize? So the ionize will be attracted to this side, right? By the anode. The anode is attracting them, right? Okay, so you can see, so they have different, so the pulling forces, right? Okay, so because they have different charge, and then so the response to the electric field differently. So the cations, they're attracted towards cathode, and ionize are attracted towards anode. But how about neutral compound? The neutral compound has no charge, so it's not affected at all. So then you have to ask, then how can the neutral compound move? So are they like moving? So are anide and ionize and cations, they move the opposite direction, and then neutral compound just remain there, like not moving? No, remember we say everything, actually in CE, everything, doesn't matter it's a cation, anion, or neutral compound, they all goes to the detector side. Now, that is caused by electro-osmotic flow. Electro-osmotic flow is the migration of the buffer solution, okay? The movement of buffer solution just drag whatever inside the buffer medium to the detector side, to the destination side, to the end side, okay? So it's so for everything, like say, even EP for the cation is to the cathode, and even the EP for this ion is to the anode. However, they all have a EOF, okay? And their EOF is the same. So the cation has an EOF, and anion has an EOF. And the EOF, so of the negative ion equal to the EOF of that positive ion. It's the same. Yeah, because it's a response to the movement of the bulk solution. So it's the medium that is moving. So bring all these ions inside, move together with it. Okay? So under normal condition, so the buffer move towards where? Move towards the cathode. So, and this tend to sweep whatever things, all the species in that direction. And then, so the detector is put close to the cathode. So, and then, so when they pass through the detector, which normally is a UV visible detector. So if your compound has chromophore, okay? So if not, so you can use indirect measurement to make the medium to be like have the UV visible absorbance, and then the compound which without to have the dent, right? Okay, we can measure that in IC, and then so got measured. Okay, so these two very important. So that is the fundamental principle of the CE. Now let's take a close look about what exactly the electrophoretic mobility and electro-osmotic flow. So what are the parameters that influence it? So how we can determine them. So, and mathematically we can see the electrophoretic mobility can be described by this equation. Again, so probably I should write it in a more easier recognized way. How about we do this one? Q divided by 6 pi viscosity R. Okay, so, and here you see this again. Q to R ratio. Q is the charge, R is the radius. Again, so now we are talking about the ions, the molecules in aqueous buffer. In aqueous buffer, again, this radius is what kind of radius? So it's the bare ion radius, A, bare ion radius, or C, or B, the choice B is hydrated ion radius. Which one? Is the ion radius itself, or like the hydrated ion radius? Which form do you think? A or B? Hydrated. Very good. Thank you. Very good. So it should be hydrated. It's the same as what we talk about in ion chromatography. Okay. So here it should be hydrated. This one is something you have to really pay attention to. So, and then again, so it's again depends on the charge density, but it's the charge over its hydrated radius, because now it's again in the buffer solution. So it's solvated, it's hydrated, okay? It's not showing up as a bare ion, okay? And also it's related to what? It's related to the viscosity, okay? So that means the less viscous the buffer solution, and then so it has what? Larger, it has the larger electrophoretic mobility. And we can also calculate electrophoretic velocity, and it determines how rapid this compound can migrate under the influence of electrical field, right? Okay, and then that's why it's time this mobility with the electrical field. So it's just the magnitude of the electrical field applied. So it can be voltage, okay? So it can be 30 kV, depends on which unit you use. You can use volts or kvolts, right? Okay, so like that one. So, well, and therefore it's easy to understand. So based on that, so we can have some idea on which ion will come out first. Okay, so how about again, so we think about, we're still thinking about a group of ions, because this one is a little bit different from IC. IC, we say if we're talking about affinity to the column, so the single charge, the double charge is definitely much stronger than single charge, monocharge one, but not really case like in capillary electrophoresis. So for capillary electrophoresis, let's just look at one single group of compound. Okay, so we just like look at the ion. Let's just look at the alkaline metal. Okay, so like for lithium, we talk about sodium. For potassium, how about we just talk about these three first? Makes things easier, right? Okay, otherwise do remember. So how about the radius? The radius for the bare ion we know is increasing from lithium to potassium, right? Okay, and we know that. So therefore, and then this one lithium ions, say not charge density attracts more, maybe water to around it molecule, and then so if it's looking at the hydrated radius, so it's this way, right? Remember we talked about that in IC, right? So how about the Q over hydrated radius? Okay, so which one is larger? Which one is larger? And then definitely this order, right? Okay, so and then potassium will have a stronger charge to radius ratio. So then sodium, then lithium. How about mu EP? Anyone can tell me which one is the largest? You just tell me which one is the largest. Mu EP. Anyone can tell me the electrophoretic mobility? Lithium, sodium, potassium, which one? Potassium, very good. So potassium has the largest mu EP. Okay, now still remember, so for cations, so it is attracted to which end? To the cathode, right? So for the cations, they're extracted to the cathode. There's like this one. So this is a column, and then so this is detector, and here this is the cathode. Okay. So this is anode, right? Okay, remember that we do this way. Okay. So and then so for those, we say for those positive ions, for the cations, so they have, let me write it here, probably I do this way. So like for example, for potassium, right? Okay, it's positive. So its EOF flow is this way. Anyway, the bulk phase solution is moving toward the cathode, everything towards cathode. How about its electrophoretic mobility? It's also here, right? Okay, so this is for potassium. So probably I need to write, maybe I write the other way. It's easier for you guys to compare. So probably I do this way. I do like lithium again. I just do it right here. Okay, so the lithium, potassium, maybe I do this way. So the lithium, sodium, potassium, the EOF for each of them is the same. Is to have the same EOF, right? Okay, because the movement of bulk solution. But how about the electrophoretic mobility? We already know that. So EP, potassium is larger than sodium and is larger than lithium. Okay, so how about the overall mobility? Can anyone tell me? How about the overall? The overall mobility, we say apparent mobility, which equal to mu EOF plus mu EP. And obviously, which one is the larger one? Which one is the largest one? Of course, potassium, right? Of course, potassium is the largest one. So now, can you tell me? So if we talk about the mu EP, and then so that will be the mu apparent Potassium will be larger than mu apparent. Sodium will be larger than mu apparent. So lithium, right? So now can you tell me, so which one will comes out first? These three ions. Now, which one will comes out first? Because everyone should go to the cathode. Everyone should go to the cathode. Now, which one has the largest mobility? Potassium, right? Okay, so now potassium is running fastest because it has a larger EP. EOF is same for everyone. EOF just carry everyone away, just guarantee they can go to the end, okay? But EP differentiate each other. The one with the larger positive charge density travels fastest. The one with the smaller one, charge density, travels slower, right? Understand? So here, what you're going to see is you're going to expect in the chromophore. So what you're going to expect in the chromophore, so we just do not really look at this one. So what you're going to see, I think we just compare with same group, it'd be easier. So you will see that. So potassium comes out first, and then sodium, and then lithium. Okay, understand now? Everybody understand? Okay, so now another question is, now we just talk about the cations. Can anyone tell me, how about ions? Are they coming out before the cations or after the cations? Can anyone tell me? How about those negative ions? I can analyze the same time. Where do they come from? After. Very good. Why after? Because now they do not have this acceleration speed, because like this one, because for the cations, this electrophoretic mobility is like pushing them to go to the end, right? Okay, accelerating them to the end. But however, for ions, their EP is in the reverse direction, the opposite direction to the EOF. So that means the EP is actually pulling them back, make them travel slower. Okay, so that's why. So that's why you will see the positive ions comes out first, and then in between will be the neutral one. Okay, the neutral one, because the neutral one, okay, anyone can tell me, how about for the neutral one? The neutral one only have what? Does the neutral compound have EP? Yes or no? Does the neutral compound have electrophoretic mobility? Yes or no? No. Very good. Yeah. Because of what? Because they're not charged. They're not charged, neutral compound. They're not attracted to cathode. They're not attracted to anode either. Okay. So for the neutral compound, you can see here. So here we say it's neutral compound. So they no acceleration or no pulling. So they're just in the middle. So can you answer another question? So if I have multiple neutral compounds in this simple run, can those neutral compounds separate from each other? Can they? Yes or no? If I have, say, 3 neutral compounds in this mixture, can just using this simple computed electrophoresis, can they separate from each other? No. Very good. Because who did this separation? Who makes the separation happen? Electrophoretic mobility. Very good. So for the neutral compound, it's very important. Neutral compound, the neutral compounds, so they only have what? Only have EOF, no EP. The reason for that is because they have no charge. Okay, so that's why they cannot be separated, but because no EP, but they can travel to the end site. Understand now? Okay, so that is one thing. Very good. So we start talking about this one. You guys understand this perfectly. Okay, so now you know illusion order. So look at this illusion order. Recall what you have learned in ion chromatography. In ion chromatography, when we are analyzing lithium, sodium, potassium, are we seeing same illusion order? Or do we see different illusion order? Does the illusion order, so in CE, exactly same as what we see in cation exchanger ion chromatography? No, it's opposite. See that? It's opposite. Why? Why is opposite? Why is opposite? Okay, again, look at here. So in ion chromatography, we also look at what? We also look at what? We also look at the charge density. We also look at the charge to hydrated radius ratio. Okay, so we see potassium has larger charge density. Hydrated potassium, ion has larger charge density, hydrated sodium ion than lithium. Okay, so that's why. So potassium has a stronger affinity to the colon, right? Than sodium, than lithium. And then which one is the easiest one to be eluted, to be washed out? Which one in IC colon? So because the potassium has the strongest affinity among these three, affinity to the colon, so it will be more difficult to wash it out, right? To elute it out. So, and then now lithium has the weakest affinity to the colon because it has the smallest charge density, right? Okay, and then it will be the easiest one to get eluted. Understand now? Don't get confused. Don't get confused, okay? So although it all really depends on the charge density, the charge to hydrated radius ratio. But in IC, we look at the affinity. We look at the affinity to the stationary phase in ion chromatography. Okay, so the one has large charge density, have stronger affinity, more difficult to get eluted. Okay, so that's why potassium comes last, lithium comes first. But now in CE, we talk about the one with larger, so charge density has the larger acceleration rate. So it has more force to pull it to the end, to accelerate it, make it running faster. Okay? So here, not talking about any affinity to the column. No, we're talking about the movement in the medium. So the charge density larger will make it have a larger acceleration speed and then so traverse faster. Understand? Now, okay, so you can see that. So the cation, the illusion order is opposite to what you see like in IC. And then how about the I9? How about I9? So shall we talk about now or let's save it? Okay, how about that? So let's save it. Okay, so think about, or maybe you can think about yourself to see what's the illusion order of the ions. So on this condition in CE, the illusion order, like say, still fluoride, chloride, fluoride, chloride, and bromide. So how about their illusion order? So are they will be the same as in IC or will it be different? Okay, so think about it and try it. Well, so now let's go to the fundamental. So, and then so why? Why? Yes, similar to IC, very good. Very good. Okay. So let's look at the fundamental. So why we have this electro-osmotic flow? Why is that? So how did that happen? So why you told me that all the ions and neutral compounds all go to the destination vial. So I should know what happened. Well, so we mentioned about so electro-osmotic flow. So it's observed when the electric field is applied to a solution, and also it's due to the movement of the bulk phase. But why the bulk phase they will move? It is because you use the fused silica column. Okay, so first one, fused silica column, capillary column, actually other can do, but this one, let's talk about the traditional one. Okay, so the fused silica capillary column, we say the silica has what? Silanol group, a lot of them, right? Okay, so a lot of them. So you have a capillary tube is like this. Okay, so inside, so it has, so all this like say silanol group like pointing, so inside. Can it be? Yes, it can be, right? Okay, so now we just like show it in the so cross section. Okay, so it's intersection, so show this way. Okay, but actually it's like say it's a circle. Understand? Okay, actually it's a circle. So and what happened is like say, so when a buffer solution, so it's placed inside this capillary, and if the pH is higher, if the pH of buffer solution is higher than 3, and then so this silanol group, they start to get ionized. They start to lose this hydronium ion and become negatively charged. So as we expected, if we continue increasing the pH of the buffer solution, if when the pH is larger than 9, which is really basic, so and then all this silanol group, say they almost fully ionized. Okay, so what happens is like say when a buffer solution is applied to this fused silica capillary, when the pH of the buffer solution is larger than 3, and then so the inner wall of this capillary tube start become ionized. So because the silanol group, they start to losing hydronium ion and become charged. And if the pH is larger than 9, almost all the silanol group, they are charged. So that means that inside, so it become so negative charge. It has a large number of those negatively charged group. So, and the ionization of this capillary wall, then so we that's why we normally do it, as I say, before we run the sample, before we start using a new capillary column, we often run a kind of alkaline solution, a basic solution, just through the column first to make sure so that capillary wall inside is charged. So normally what we do is that we're going to run the sodium hydroxide or potassium hydroxide through the capillary column first, and then so make sure so inside they are charged. Okay, so that's why we say under normal condition, so both anions and cations and neutral compounds, they migrate towards the cathode. This occurs because the capillary wall, the inner side of the fused silica capillary wall, is negatively charged. Okay, so when it is exposed to a buffer solution, so that with pH larger than 3, and if its pH is larger than 9, so it's almost fully charged. And then what's next? They say, okay, I know it's charged. And then what's the point? What the point is, because now you're running the buffer solution after you run the alkaline, right? Okay, so you are your real, like say, so analyzing buffer solution. So in your buffer solution, it has positive ions and negative ions. So the positively charged cations of the buffer solution, now they're attracted towards where? They're attracted towards the negatively charged cyanamide group on the wall, right? Okay, and they're going to form two inner layers of the cations, as you can see in this figure. So the first layer is called fixed layer. Why? Because those cations, they're more tightly bonded or tightly attracted to these negative sites on the wall, but they are not really, like, say, 100% neutralize this negative charge. Some of the cations, they are loosely bounded. So they are loosely attached to the negative charge. So they're in a mobile layer, therefore. That means they're in a mobile layer. So they're a little bit further away from this, the cyanamide group. So the mobile cation layer, well, because they are what? They are the cations, they are solvated, they're hydrated, okay? So, and then the mobile one, because this one, overall, can anyone tell me? Can anyone tell me what is the overall charge of this mobile layer? Is this electrically neutral or is it positively charged overall? Overall for this mobile layer, is it neutral or is positively charged? Overall, I mean the lead charge. The lead charge of this mobile layer is positive. It's positive, okay? Because overall for this double layer, so they need to be neutral. Because in this double layer, two layers, the amount of the cations in these two layers should equal to the total negative charge in this double layer. They have to make it to be neutralized. Okay, understand? So, and some of them already, like, say, so firmly attached to the first fixed layer. Some of them loosely bounded. The total amount equal to all these negative charges. Okay, so this layer, so is positive charged, net charge. So it will be attracted to what? It will be attracted to the cathode. Okay, so the whole layer here, because of the cations, they're attracted to the cathode. And because all these cations, so they are solvated. So when this mobile layer, the whole mobile layer, is moving to the cathode, and then because not forgot, we have another layer. So on the top is actually something like this one. So this is a bulk. Oops, like this one. This is a bulk solution. And here, so you have the mobile layer. Fixed layer. So this is mobile layer. You can see mobile layer. Okay, it's like that one. So the mobile layer, whole mobile layer is pulling, is moving to the cathode, and it will solvate it. So it's therefore it's dragging. So this one is also another layer here. So they're dragging the whole bulk phase to go together with it, to go to the cathode. So this is how. So let me mute. Sorry. 1 minute. Do that. Okay. So this is how. So why it got electro-osmotic flow. Okay. So it's because of that one. So let's take a more close look about this double layer. Okay, you can see that now it's on the capillary wall. It has excess negative charge. So that just align and densely align. So on the wall, and now so you have the double layer. So this one is the stern layer. It's also a fixed layer. That means a fixed layer. So and then the cations more tightly bounded to the stationary phase, to the capillary wall, not stationary phase, sorry, to capillary wall. And then it's a diffusion layer or mobile layer. And then the cations, they're more loosely bounded. Okay, so you can see here, they're more loosely bounded here. So, and then, so, and overall, we can see that the total charge, positive charge, so in this double layer, they should be able to neutralize so all this negative charge. So in this section, okay? So the net electric charge, so in the those layer. So it should be equal to that one. So, and then we can see, we can calculate electro-osmotic flow, and then electro-osmotic velocity, EOF, be equal to electro-osmotic mobility, mobility, this one, times the electrical field. And then we can see that. So the electro-osmotic flow is related to what? Related to zeta potential here, the zeta potential, and also the permittivity of the solution, and something we have seen that before, viscosity. Okay, so what is zeta potential? Let's take a look. It shows that. Here shows the potential. So originally have on the wall, okay, because it's negative charged. So, and because already have some cations, so in the fixed layer, so they neutralize the charge on the wall to make the total net pressure drop, okay? So, and the zeta potential is a potential drop across the diffuse layer. So that means it's the pressure drop in this mobile layer, okay? In this mobile layer. So it's easy to understand. So if you're having a higher pH, for example, so if you increase the buffer solution pH from 5 to 9, what happened? If you're using a high pH, and then so high pH increase the pH, first, what will be increased? There will be more charged negative site on the capillary wall, right? Yeah. So, and there'll be more negative sites available. When there's more negative sites available, what happened? And then so that will be the higher electro potential here, right? Okay. So because more charged. And then, so because you have fixed layer, the buffer solution, so neutralize some, and then, so, and then you have more that extra you need to neutralize. So in this what? In this diffusion layer. So obviously you can see that the zeta potential is proportional to the charge on the capillary wall. If you increase pH, more charging site on the capillary wall, and then so that will also increase the zeta potential. Okay, so when the zeta potential increase, what increase? Electro-osmotic flow increase. Okay, so that is one thing you can see. So the zeta potential is actually directly proportional to the charge on the capillary wall. As pH increase, the charge on the wall increase, the more charging site. And then, so because the mobile phase will just like say neutralize part of it, okay? So, and there'll be still like, because more charge, more need to be neutralized, and then so more will be left for the diffusion layer to neutralize, and then so the higher zeta potential and the higher EOF. Another one is like say, it's also proportional to the thickness of the double layer. What does that mean? The thickness of double layer. So it's actually kind of called what? It's really related to the ionic strength. It's related to the concentration of a buffer solution. How to understand that one? Let's look at it this way. So I just try to help you guys to understand. So now, if I have the concentration of the buffer solution, if it increase, okay, for the buffer solution, for the cations, if the, so I say if the cations, okay, cations, not calcium, for the cations, so increase, how about I do this way? If the concentration of this one increase, if the concentration of the cations increase, so, and can anyone tell me, so, and then are you going to have more cations in this fixed layer or less cations? If the concentration of the cations increase, if the ionic strength of your buffer solution increase, that means the concentration of the cations in your buffer solution increase. So you will have more or less cations in the fixed layer. You will have more. Very good. Thank you. You will have more cations in the fixed layer. And can you tell me, and now, so the pressure, the electron potential drop in this fixed layer will be here, point A, or here, point B. Can anyone tell me? Now, because now you have more, you will have more cations here to do the neutralization. Okay, so can anyone tell me now? So the potential drop, so in this fixed layer, so it will come to A or come to B? Come to B. Very good. Very good. Okay, you see that, because then more to neutralize, then they will drop more. Okay, will drop more. And can anyone tell me now the zeta potential decrease or increase? Now the zeta potential decrease or increase, because zeta potential means the pressure drop across that diffusion layer in this area. Okay, sorry. So can anyone tell me now the zeta potential decrease or increase? The zeta potential decrease. Very good. Okay, now do you understand now? Because then more to neutralize, and then so the potential drop in the fixed layer will be more. And then, so that's why I would call this one prime. So the zeta potential then will decrease because the pressure drop across diffusion layer now will be less, right? Okay, so easy to understand. Good. So, and then you can see that. So it's proportional, zeta potential is proportional to the thickness of double layer. As ionic strength of the buffer solution increase, so this cation, more cation available in the fixed layer to neutralize the charge. And then, so more drop, so potential drop in the fixed layer. And then there will be the less pressure, less the potential drop in the diffusion layer. So that means, so the zeta potential will decrease. Okay, decrease. So now, so that's easy. Now let's take a look about what are the parameters so that can influence the EOF. We finish this part. Okay, so first, let's look at how pH influence. If you do not look at the notes, think about it by yourself. pH, how does pH increase? Higher pH, more charge, right? Okay, on the wall. So because more sunlight group get ionized. So you can see this is a relationship between the pH and EOF mobility. We can see it start at 3 because now the sunlight group start be ionized, and with increasing pH, more sunlight group ionized, and then it's about pH equal to 9, and then so about almost fully ionized. Okay, so that means if you increase the pH from 3 to 9 to 10 to 11, okay, and then that will increase the number of negative charge on the capillary wall, and of course, and then that will increase that electro potential, right? And then so high electro potential drop then in the mobile phase, and then that means you have higher zeta potential and you have higher EOF. Okay, so how about ionic strength? Okay, let's just talk about it. If we have higher ionic strength, that means you have more cations available to neutralize so the negative charge on the wall, right? Okay, you have more cations so in the fixed layer, and then so that lead to a smaller zeta potential, and then that will be the lower EOF. How about temperature? Oh, you didn't talk about temperature before. Okay, but remember here, What is that? Viscosity. Do we see viscosity in electrophoretic mobility? Yes. So mu EP, remember, is also proportional to what? It's also proportional to the viscosity, right? So mu EP is also proportional to that. Okay, and then, so that means increase the temperature, so and we reduce viscosity. Okay, at the same time, so make the stern layer, the fixed layer, less stable. And some of the tides in the fixed layer may escape, go to the mobile layer. Okay, and then so that could cause the higher zeta potential if you increase the temperature, and then zeta potential increase, and then the viscosity decrease, and then you have less resistance, and then so the EOF increase. Okay, understand that now? Yeah, and same if you increase temperature, the viscosity decrease, and also you have a larger EP as well. And sometimes also people can add some organic modifier into that. So that can change the viscosity of the solvent, some of organic modifier. And also even people like sometimes for other application, they add the surfactant into the mobile phase. That can even change the charge on the wall and then so make that illusion totally reverse. Okay, so that could happen. So, but when we say, if I say, can you provide 3 factors that influence the EOF? Kind of pH, ionic strength, and temperature. How can they influence? This is how they influence. Okay, so and that is pretty enough for now. So let me look at the time. So how about we take the break today for 10 minutes, okay? So we'll come back at 20:03. Okay, so 10 minutes break first. Okay, so let's start again. So, and we talk about that. So, and let's just kind of like wrap up what we have learned for, sorry. Okay, it's here. Sorry. Okay. So we just finished talking about, so what is the EOF and what influences the EOF and what is the EP and what determines EP, okay? So now, so let's just put them all together and then and kind of like an overview of this apparent, the total mobility. Okay, for any given solute, the apparent mobility equal to mu EOF plus mu EP. So it's just like the electroferrite mobility plus electro-osmotic flow. Okay, so in general, when we talk about already, pH is larger than 3, and then so the inner side of wall will be charged, and then so it generates the EOF flow. And when pH, so like say this one pH so larger than 7, so the EOF flow is already pretty strong. Okay, it's already strong. And then so if the pH even further and increase to 9 or to 11, so then so the capillary columns are inside in the wall almost all charged, and then it will be very large EOF flow. And in general speaking, so the EOF flow under this kind of condition, so they're much larger so than EP. Okay, so just make sure that guarantee that everything goes to the detector part. And then so when we talk about the positive ions, because they are attracted to cathode, which is same direction as the EOF flow. And then so that's why the apparent velocity equal to E mu plus EOF. And then however, for negative ions, because they're attracted to the I node, which is opposite to the EOF flow. So that's why the apparent mobility equals to the EOF mobility minus the EP mobility, okay? And however, neutral compounds, because they're not charged, so they do not have any EP, do not have any electroferrite mobility. So they only have EOF. So if we sum it up, you'll see that so the apparent mobility of positive ion, so that's larger than neutral compound, okay? So, and then larger than negative ions. So, and then so under normal condition, under the very most simple capillary electrophoresis, we call that capillary zone electrophoresis, and then we are expecting the cations comes up first, and the neutral compounds not able to be separated from each other comes in the middle, so as about peak, and then followed by the anions. Okay, so that is that. And then we already mentioned that, we see that for cations, so they are eluted, so at reverse order as what we see in IC. And for anions, we see that exact same order, right? Okay, so separation based on, yes, this is what we see, and then separation based on electrophoretic mobility, okay? So, and the sequence of elution, so at the cathode, so in the case of predominating EOF, that means that in the case of the very large EOF, in the case of the, oops, what happened? Can you guys still see? Let me try one more time. Yeah, I dropped out. This one? This one? Yeah. Can you now see the page? You can, right? Okay. So because I say accidentally, so get out. So that means like mu EOF. So mu EP, this condition. So cations look first, followed by neutral species and anions. Okay, so if you look at this way, so you can see if it's the 2 plus 1, so if we look at this, the charge, that means that actually we're talking about if the same size, okay, if the same size, but Q is 2 plus and then 1 plus, and then neutral, and 1 minus, and 2 minus. So that means this is the largest Q to R ratio. So we assume like the same radius. So same radius, okay, here. So that's why. So you can see that. So, and everybody has the same mu EO. So that's why you see this blue arrow. They are same length because for everyone it's the same. Okay. And then so how about for mu EP, which is the gray one? Okay. And then the one has what? Has a large charge density, positive one has the largest mu EP, followed by so the one with smaller one. And then so the neutral compound has no mu EP. Okay, so no mu EP. But new one, no. Okay, and then for -1, so the more highly charged negative ion has a stronger mu EP towards the opposite side. Okay, and then so the smaller one has this way. So that's why if we add these two together, so now I erase that. So if we add the blue one and gray one together, we can see, so that's one. We see the largest mu apparent. So for this highly charged positive ion, followed by, so this like, so smaller charge density one, and then by neutral, and then, so the one with more intensely, so the highly charged negative ions has a stronger pulling force, and then it comes out later. Okay, so for that, you can expect that one. So for this one, you can expect that. For fluoride, bromide, chloride, okay? So fluoride, chloride, bromide. The bromide definitely, so this one, so you have what? So you have the stronger pulling one. So bromide will comes out after chloride, after fluoride, right? Okay, so and then we can put that on. So the total velocity, so that is the velocity equal to the mobility times the voltage, applied voltage. So the applied voltage can go up to 40 kV. Normally it's just 30 kV. That's pretty common. So and then so that mu EP plus mu EOF times V over the length, because electric field, so it's voltage divided by, voltage by the length. Okay, so voltage divided by the length. So and then so L is the distance. So this one. So L is the distance between the injection and detection point. Pay attention to 2L here. One is the small L, one is the bigger L. Okay, remember what you see here. Okay, A, B, C. A, stop point, B, end point, C, detector. So which one is the big L? Is the total length of the capillary. But however, if we're looking at the electrophotogram of this one for this CE, so the total length for the migration from the stop point to detector, which is AC, is the length for the ions that have traveled to reach the detector, right? Okay, so that's why you see the small L is the distance between so the injection point and the detection point, small L, and then the big L is the total length, okay, so of the whole capillary tube. And then V is the voltage applied, which is normally like 30 kV, 40 kV, and mu is apparent mobility. So we can see that from there, we can see here, if we have the larger voltage, what happened? If we have applied a high voltage, so you're going to have a faster separation or slower separation. If you apply a high voltage, and then you're going to have a faster separation. If you apply the high voltage, you'll have the faster velocity. And then, so you have the shorter migration time. So short time for the run to finish, right? Okay. So look at this one. So you can see here. So the kite time moves first based on charge to size ratio. Largest one first, and neutral one so comes out later. Okay, so and also then anions later. And let's look at this one. So the resolution actually of this analysis is also related to mu EP and also related to voltage and diffusion coefficient apparent velocity. So we can see if we increase voltage, now there's no pump. Driving force is this voltage electric field. So if we applied high voltage, I mean like the high driving force for the whole chromatograph, right? Okay. And then so that actually can help to increase what? Resolution. Okay, can make the separation efficiency increase and can make the separation time decrease. Okay. So does that mean like the higher the voltage, the better? Can we just like increasingly, so increase the voltage? Think about that. Think about that, whether that's reasonable or not. So can we just like keep increasing voltage? Can we do that? Well, think about it and we'll see. And now we already know that. So we just know, we have known the relationship between the migration time and also the voltage and apparent mobility. Now let's think about some questions together. Okay, now you have this, so capillary electrophoresis, we call that electropherogram. Okay, it's called the electropherogram. It is electropherogram. Okay, you can see it's a plot of the migration time. So here is a migration time. We call that migration time. So you can see it's expressed to seconds. Okay. Versus the detector response. Here just using UV. But it needs to be something like can have UV absorbance. Can be fluorescence as well. This one can be conductivity as well if you're using ions. And also can be mass spectrometer, can use that one as well. Okay. So, and this is such a very typical electropherogram. Okay. So you can see like those 5 peaks that are separated from each other. So we can ignore that. I already know that the number 3 is a neutral compound. So their migration time is 600 seconds. Okay. And also the others, the migration time for all the others are shown here. So now I give you, I have the small L, so which is 50 centimeter. I have the larger L as the total length of capillary, which is 57 centimeter, because the electric field is applied to the whole capillary tube. Okay, voltage is 30 kV. So can you calculate? So the apparent mobility, so the electro-osmotic flow, and also the electrophoretic mobility for each peak. So I want you have the unit of mu of them can be centimeter square per volts per second. Okay, can you guys, can you try that by yourself? Try it by yourself. Try it by yourself first. I just give you L, small L, larger L, velocity. Okay, and I want to calculate mu AP, apparent one. Also, I want to calculate EO EP, EOF EP. Now, that's easy because from what you showed me earlier, I already know that time equal to, so the total length divided by velocity, so which equal to, oops, I already know that. If I put the time in, I should be able to calculate the mu apparent mobility, okay, for each one. So, but how can you know the mobility of electroosmotic flow and electrolytic mobility? So which one do you need to start first? Can anyone tell me what is the starting point? Now you have 5 peaks. So which peak is the one you're going to calculate? Neutral one. Yeah, number 3, right? Why? Tell me why neutral one? Because now the neutral one, the mu apparent mobility equals to what? The apparent mobility equal to EOF. Very good. That's the starting point. Good. So, and now your classmates already give you the hint. So can you start calculating that, trying that by yourself? I'll give you 5 minutes, okay? So, starting from number 3. So everyone try that by yourself. Try that by yourself. Pay attention to the sign, positive sign, negative sign. Pay attention to the unit. Okay, now I'm using centimeter square per volt per second. And we start from peak 3. How about we do peak 3, peak 2, and peak 5 first, okay? So after you finish peak 3, and we can try peak 2 and peak 5. I already did this one for peak 3. I get the apparent mobility for neutral compounds. And I know that for neutral compounds, they only have electroosmotic flow. They do not have electrophoretic mobility. Okay, and then I got, that means from that, I already know what is the EOF. And EOF. It's same for everyone, right? Okay, it's same for everyone. So that means I already got the EOF for pick 1, 2, 3, 4, 5. It's the same. Next step is so straightforward. So if it's talking about the peak 2, so we can calculate the apparent one. It's easy, so we just put that in. 50 times 57 divided by 30,000 times 500. Okay, so we can get that apparent mobility is 1.9 times 10 to the minus 4th, right? Okay, so I'm not writing the unit first now, and you get unit, okay. And then so mu EP for peak 2 will be apparent mobility minus mu EO, because we already know that. So, and apparent mobility equal to mu EP plus mu EO, right? And we got that 1.9 minus 1.5, got 0 here, 8 equal to 0.32 times 10 to the minus 4th square centimeter per volt per second. Okay, so here also you need to add the unit. Okay, so that is my pick 2. Agree? Do you get the same answer? Do you get the same answer? Okay, if you can get the same answer, that is good. And then I'm going to calculate pick 5. Okay, oops. So I got the peak 5, and I got apparent 1 equal to 50 times 57 divided by 30,000 times 900. So I got this one equal to 1.06 10 to the minus 4th square centimeter per volts per second. Pay attention to the units are, because if you're using different things, will be different. Okay, so and then so I got mu EP so equal to, so again apparent mobility minus osmotic mobility. I keep jumping back, and then that will be, so I write it down here, 1.06 minus what? 1.58. So times 10 to the minus 4th. So which equal to negative sign here, okay? 0.52 times 10 to the minus 4th square centimeter per volts per second. I point out the negative sign here. What that mean? The negative sign means its direction. Its direction. Its direction is pointing to the anode, okay? So because this is the ion, so the ions, so its electromobility has different direction as the cations, okay? So that's what I get. So do you get the same answer as what I get? Yes or no? So yes, same. Very good. Very good. Okay. So That is very smart. So, and that means you already like mastered this part. So very well. I think by now, so you must understand what is EOF, what is EP, right? Okay, and you understand why so electrophoretic mobility can separate the ions. So you will understand why electro-osmotic flow just sweep everything to the detector side. Okay, and you also know so how we get different so mu EP and mu EOF. Mu EOF is the same for everyone. So where we get different apparent mobility and also different, like say, the electrophoretic mobility for different ions, right? Okay, and so how does that relate it to voltage? How does that relate to the Coulomb length? And how that relate to the migration time, right? Okay, so if that is good, that's good. So, and then so for number 1 and number 4, so you can try by yourself and you can calculate by yourself at home. Okay, so and after class. So if it's fine for all these parts now, so I'm going to move on. Okay, I'm going to move on. Okay, so we're coming back to this resolution part. So this one, we're coming back. Okay. And we see that we already mentioned at the very beginning. I said the very obvious difference of the capillary electrophoresis and conventional HPLC is what? Is that they apply different Coulomb, right? That's one obvious one. So the capillary electrophoresis apply a capillary fused silica capillary tube that is like the GC one, but much shorter. Okay, but then that's why. So it's the capillary format, actually the Coulomb so used in CE. So it has its own advantage. So it has a reason to use that kind of capillary Coulomb. So it's actually can minimize many sources of the band broadening that occurs in a conventional HPLC. Okay, so one of the key feature, first you see, if you look at the EOF flow profile, you see that. So the EOF flow profile now in this capillary Coulomb is not parabolic. It's a what? It's a flag. Okay, so it's a flat one. It's like a plug. So why the EOF, electro-osmotic flow? It has a plug profile, moving profile, flow profile. So it is because now the driving force in CE is not a pump. The driving force in CE is not a pump. Okay, so and then the mobile phase, the bulk phase is moving by what? It's moving because of what? Because of the electric field applied, and also because of what? Because of the negative charges in the inner side of the wall, right? So you can see that because of negative charges, and then that helps the formation of what? That helps the formation of the double layer, So you can see the negative charge, they're uniformly distributed along the capillary. So that means what? That means, I say, when the mobile layer move that way and drag everything onto the cathode, it has no pressure drop because no pressure applied yet. It just has the pass along the wall because it just has the negative charge uniformly distributed along the capillary, and then so you have those mobile layer, not mobile layer, just like say uniformly distributed along the capillary as well. Okay, so then therefore the flow velocity is uniform across the capillary. So that's why it has a plug. It's a plug. So however, for the common HPLC and GC, for HPLC, like say, we have what? We have the pressure. And then so when the flow goes through the packed column, and then the friction forces at the column wall cause the pressure drop, hold it back. Okay, and then so that's why, so the flow in the middle is travel faster. So then the flow and along the wall, and because of that frictional forces, and then so that makes the peak broadening. And we call this kind of shape of this hydrodynamic flow, we call that also called parabolic flow profile. Okay, because now CE has the plug one, so there's no pressure drop, and then the speed is uniform along the capillary. So we have, therefore, so it has minimized the broadening, peak broadening, and then that can lead to excellent column efficiency, and also and very good the separation efficiency. Okay, so and it can even allow separation on the basis of mobility differences as small as about, say, just 0.05%. Okay, so that is one advantage of using this capillary. Okay, so you can see that minimize the peak broadening, and less peak broadening efficiency, we say increase. Okay, so next one is here you apply a high voltage along the capillary, and because the medium now is a buffer solution, so they're electrolyte, right? Okay, so they're conductive media, so an electrical current actually is passing through this conductive electrolyte buffer. So and then what happened, then it will cause, like, say, the Joule heating. The heat will generated within the capillary when the voltage applied. So and then so that means it need to dissipate. You have to dissipate the heat so through the capillary column wall, through the surface. If you're using a very wide column, not a capillary column, and then so you will see that temperature gradient. Okay, so like that one, temperature gradient. So and so happen along that inside, so along that cross section. So and then so if it's like, say, you see a temperature gradient form across the capillary diameter, so and then that will lead to what? Because different temperature, and you have the convective flow, right? Convective flow. So within that, so buffer solution inside the capillary, and then that can cause the peak broadening. So then peak broadening, and then that will lose this resolution. However, what you have done now you're using capillary, so it's very fine inside, it's very tiny. Okay, you're very thin, and then so that means the heat generated can be dissipated effectively through the capillary wall, and then not really forming very obvious the convective convective movement. Okay, so and then that reduce this kind of convection related band broadening, so that encountered using a traditional like wide peak, and then so that can greatly actually also help for the peak efficiency increase resolution. So and then so that means because of capillary, so they more effectively dissipate the Joule heating generated inside the buffer medium due to the high voltage, and then so that reduces the convection related band broadening. So and then so that increase the separation efficiency. Okay, and also for this one, so we try to avoid that overheating. So you don't want very high temperature, because a high temperature can cause thermal degradation of those temperature sensitive analytes, such as the protein. Okay, so to minimize this kind of the Joule heating or overheating, so there are actually several things we can do. The first one is then you can reduce the voltage. How about you reduce the voltage? If we reduce the voltage, so what happened? Remember we just mentioned here, if we reduce the voltage, and then we'll sacrifice what? Resolution, and you have longer migration time. Okay, seems not really good, right? Okay, so and then so that's why. So here they're using a thinner capillary, as I just mentioned, that also help to solve this problem. So small diameter, easy heat dissipate. Okay, so that's why capillary tube do that. And also, and for capillary tube, it can get into the detector, can have the on-column detection. So and then so for that one, just scratch the coating on the capillary fused silica tube, and then a portion of the capillary is used as a detector, so which also eliminate the post-separation broadening owed to that volume or connection. So you can see that. So this capillary format employed. So in capillary electrophoresis, so really improve the peak efficiency in multiple ways. Okay, so this is one thing. So why we call C is high efficient, so separation. Okay, and if you look at this one, so and this is a capillary electrophoresis, and this is high performance liquid chromatography. This is looking at this to separate some of the large molecules such as protein. You can see that plate number for capillary electrophoresis can be really larger than even larger than the HPLC. And the N number is equal to mu EP voltage divided by 2D. So that's why, because resolution, we know that. So it's to what? N, right? So that's why you see here. That's why, so you see here. So here, so it's to square root of N. So I can see square root of V voltage and square root of 1 over D, right? Okay, diffusion. So what does that mean? It means that, so if you increase voltage, and what happened if you increase voltage, that will help to increase the efficiency. And also, if you increase the decrease the diffusion coefficient, and then so that will help you to increase the peak separation efficiency as well. So that means, so for capillary electrophoresis, it has even more advantage about this separation efficiency when it's dealing with some large molecules, because the large molecules, the biomolecules such as the proteins and nucleotide, so they are big, and then so they have much smaller diffusion coefficients, right? Okay, so you can see, and also analyzed with a large mu EP, and then so also have a great efficiency. So, and efficiency is independent of column length, because here we did not see any term of the length, only diffusion coefficient, voltage, and electrophoretic mobility. Okay, and the N value of 100,000, 200,000 can be achieved, may even be several million for biomolecules, because they have relatively small diffusion coefficient. Well, and it's actually the peak efficient for capillary electrophoresis also generally follow that ABC terms. But just answer the question. So do you think like for capillary electrophoresis for CE, for if let's say, does it, the peak height, you know, the plate height, that one, plate height, so it's related to ABC terms, right? Okay, does it have the eddy diffusion? Does it has a term? Does it has a term? Actually, no, because the column now is not packed column, right? It's not packed column. Very good. It does not have a term. A term, no. Does it really have C term? No, right? Because now the flat, the plug, the flow format, very good. Your answer, very good. So because the flow profile now is a plug. It's a plug, right? It's like that. Okay. So it's not something like, say, paradigmic, right? We see like in the movie mobile phase. No, it's not really packed column. And then so it's not like in the GC like that way. So it's not no obvious A term and no C term. So what matters is just the B term, so related to the diffusion coefficient. Okay, so what matters only the longitudinal diffusion. That this B term may contribute diffusion, may contribute to this peak broadening. Understand? So that's why. So the peak efficiency of the CE is pretty good, especially for those large biomolecules, so which has a small diffusion coefficient. Okay. So that's all for the general part. Now let's move on to the instrumentation. So the basic instrumentation of C is so simple. You guys already see that figure for several times, right? Okay, so you see that it has a high voltage power supply, which is about 5 to 40 kV volts. Okay, and the voltage is proportional to its velocity. We see that, okay, and it has high voltage, high velocity, and faster migration time. And also the voltage is related to the resolution. We see that. So higher voltage also can have higher resolution. So also you have two buffer reservoir. One is starting point, the other is the end. So one has anode compartment, the other has cathode compartment. A very simple and traditional CE, the cathode one compartment is the destination valve. Also, you have the capillary tube, so which is the column, is a fused silicon one. So this one is, we commonly use this one. And then, so we already talk about, so advantage of using this capillary column tube, how does that so help to increase that column separation efficiency? Detector can be multiple. Detector can be UV visible, can be direct way or indirect way, can be fluorescence, direct or indirect, okay? Can be mass spectrometer, can do that, and also can be like other things, okay? So, and normally we can see that, so we want to, we use that no pump, and also the sample vial is pretty small because what inject is very small. Instead of microliter, what you normally inject is 1 nanoliter, or it's just like 10 nanoliter, very small amount applied. No pump, okay? So just a high voltage. And this is typical view of this capillary tube. So you can see that capillary tube. So the ID, so it's typical about 25 to 100 micrometer, and outer diameter is about 400 micrometer. So you can see this is the fused silica is often used. The reason for that is because it's transparent to UV and visible. Fused silica is transparent to UV and visible. Okay, so because then we say part of the tube, so will be used in the detector, right? Okay, so, and you can see a coating, the polyamide coating is coated. So which is about thickness for this one is about, say, 10 micrometer for this coating. And this is used to increase the flexibility of the tube, capillary tube, not make it so easy to break. But then you ask, say, how about for the detection? You say that you have to go through the detector, and then have the online detection, so in-column detection. So for that one, so for the detection window, and this the polyamide layer must be removed either by scratch it away, or by burning it off. So, and also we want to keep the capillary tube like in some temperature controlled one. Remember, we already talked about how temperature influence the EOF. Do you still remember? So we want to put that in the temperature controlled environment, because what? Because the temperature really influences what viscosity as well, right? So, and viscosity buffer, so that of the buffer vary with the temperature, and also we say the temperature also influences zeta potential, right? Now, if a high temperature, that makes the stern layer less so stable, and also the drawer heating must be dissipated so effectively. Okay, so use fused silica. Why is that? And also, so do that. The length and small bore and thickness of the silica important. So, and that need to drawer heating, need to be dissipate that easily. To use the small ID in the diameter to reduce this problem. Which problem? The drawer heating problem. Okay. And the tube is initially filled with buffer solution. What kind of buffer solution? The basic solution. The basic solution normally, say, can be sodium hydroxide before you use it, or potassium hydroxide. Why? Okay, to ionize the inner wall, right? So of the capillary tube, to ionize the signal group. So the signal groups, right? Okay, so this is why we should go that. And then, so what happened? And then the sample is introduced by dipping one end of the sample, so into the sample vial, and then using any of the following to cause the sample to enter tube. I'm gonna say you can either apply voltage. So that's the most common one. We call that electrokinetic injection. You apply a potential voltage to cause the sample to move into the tube. But we say it's the least popular one. Why? You can also use in the hydrodynamic method. So for the hydrodynamic method, we normally have 3 ways to do that. Either can apply pressure, or either you can apply siphoning. Siphoning, you can do vacuum or gravity, right? So just like make the sample pour into the tube. You can do vacuum, or you can do that by the gravity. So why we say the electrokinetic method? So it's the least popular one. Why is that? We say that if we want to do that, we just put the one side of the capillary tube into the sample solution, and then apply high voltage over this capillary tube for a certain time. This is sound like same as what we do analysis, right? Okay. Yeah. So how does that sample get introduced then? You apply voltage. Yes. So the sample, so they are introduced, right? So they're introduced into that by its apparent mobility, right? They're all introduced by its apparent mobility, APP. So now the question is, does everyone has the same apparent mobility? Yes or no? Does everyone, every compound, every ions in the solution, in the sample, has the same apparent mobility under this electric field? No, right? No. Very good. No. So then what happens if they don't have the same apparent mobility? So for those, so who has a larger apparent mobility, so they will be injected more than those with the smaller one, right? So obviously now you see that there's some discrimination occurred about this injection process. So between those different compounds, because we already said the component with high apparent mobility are injected in larger quantity than those with the lower apparent mobility. So then that's why it's not the favored method. So, and of course you can, if you have no choice, if you still have to use that, so you try to think about minimize the influence. And what can do if you want to minimize this discrimination is just use lower voltage for injection. So then the one you use for separation. Okay, so that's one option. If you have no choice, if I have to use one. So that's why this is not really favored. So we want to use the hydrodynamic method. So hydrodynamic method, you can see this one, the first one. So the sample vial is kept, okay? And then so it precisely apply a voltage. So a precisely controlled external pressure, sorry, not voltage, pressure. Apply this pressure into the sample vial to force a controlled amount of sample into the capillary. So this is one by pressure. But also you can apply vacuum here. So instead of like apply pressure here, so instead of pressure, you can also apply a vacuum. Okay, so you can also apply a vacuum here. So and then so that will pull the sample to this direction as well. So or you do the siphoning. That means you lift the sample end elevated to a level that is higher than the destination vial, and then by gravity some of that will be injected. Okay, so and obviously they're more complicated than its electrokinetic force, so that's why even people know that it has some discrimination and bias, and they still like say apply lower voltage, use that one. So and for injection volume, it's normally say 50 or 10 or even 1 nanoliter. So that is very, very small amount, Okay, So this is a method used for detection. So how about we take a break now here again? So again, so still take about 10 minutes break, and we'll come back at 9:04. Okay, so come back at 9:04. Okay, so we're going to start again. So let's look at the detection method. You can see that it has the multiple different detection method. It has the UV visible one. We have shown that for many times for proton, so 280, and for others, so normally can be like 220 about that one. So, and it can be either like direct if we have the absorbing chromophore, or it can be like say indirect. Indirect means like we already explained that when we are talking about ion chromatography. We say that so if it's like does not have a chromophore, we can have the background. We can make the background. So to have the medium to have the UV visible absorption, and then so and for those compound, so that is not absorbing that. So you have the dent, right? It has the negative peak. And then so we just switch the polarity and it should be fine. And then so the most challenging part of the CE detector is the small diameter of the capillary tube and also the small sample volume that encountered, because you are dealing with that injector several nanoliter. So that means like say your detection method can need to be pretty sensitive. You can see the fluorescence, laser fluorescence, also uses radio metric, mass spectrometer, and then so and even conductivity. So and this one shows the UV visible, and because this one I think you have learned that probably last semester in analytical spectroscopy, because we see that because A equal to epsilon BC. So and then so if we want to increase A, so and if we want to make more sensitive, so you want to so either increase epsilon or you can also try to increase BC, the light path. And then so the Z shape of the cell. And then so instead of having the B, it's just a very narrow one. And then so you have a much longer light path, right? So by this doing this one. So the small capillary diameter results in very small B. So that's why using Z shape is used, which can increase B, the light path, by 10 to 15 times, and then you get a better sensitivity. And also there's some design. So they have the inside, they have reflecting coating so of the tube. So and under the polyamide coating, and then so and then the light path can be like say reflected for several times and then go through. So this is a tube, okay, yeah, the white one, okay, and then so and then can increase that light path. That's how it works. And then so you can see that so the strength of the capillary electrophoresis so obvious. It has pretty high speed because of a very short column, and then so and it has high sensitivity. We explain why the peak has that efficiency, right? Okay, so it's sensitivity because it deals with very small amount of the sample get injected. So it has low detection limit, and then so instrument, so it's not really costly for rounding, but the result is not really always get reproducible. Okay, so and so that part is something I say a little bit challenging. So that's why we can see that capillary electrophoresis often like we can use for some like research purpose, but like in why we put as the last topic, because you see that in the commercial lab in some commercial application. The application of C is much rare than HPLC, normal HPLC or GC or IC, right? So there are many variations of approach that have been used to deal with specific types of problems. So using the CE, so that's why we have different modes of capillary electrophoresis. So here we'll talk about so several different kinds. The one we actually already mentioned, the very basic one, is called capillary zone electrophoresis. This is the most basic one, okay? So, but we all know that it has the limitation, just what? The neutral compound cannot be separated. They just come out as the same peak because they just have the same EOF, they don't have the EP, right? Okay, so and to overcome that limitation, so that led to the development of micellar electrokinetic capillary chromatography. So it's the micellar to do that. And then so we also apply C to handle a very challenging analysis topic, that is for the chiral separation. So you add some surfactant, micelle, this one, you have to add some surfactant in to form the micelle. And for chiral separation, also need to add some modifier inside. So like CD, that one for this chiral separation. And also CE can also be capillary gel electrophoresis. This one is applied a lot for the DNA separation. And then the medium is now gel, and which is acting as molecular sieve, okay, just like different size to separate DNA based on the size. Very interesting. Oh, you know that. And also the capillary isoelectric focusing, and also is analyze the things, and there's a pH gradient, okay, and then so it depends on those isoelectric point of the compound, right? But and then today probably I hope we can finish the chiral separation. So, but definitely we will finish the first two, okay? So we just focus. We only have time to talk about the top three. Even the third one, I'm not sure we can finish it or not. Okay, so the capillary zone electrophoresis is the simplest form of the technique. So, and we already mentioned capillary tube filled with buffer solution and sample loaded, and the ends of the tube placed in reservoir, so and then so on. So, and we normally need to condition the capillary tube before we use it. We say we condition with 0.1 molar of sodium hydroxide for 10 minutes. The reason to do that, make sure the inner wall charged. And then so we wash that by water by 5 minutes, and then run the buffer solution for 10 minutes. And then so just make sure surface fully charged, and then so do that. Note, and then under normal condition, the sample end of tube is the anode, and the destination tube site is cathode. And then this one already talked about, okay? So, and however, before in the normal condition, you will see that. So the cation comes out earlier than neutral compound, than iodine. How about if we say you just want to analyze ions, you want to make the negative ions comes out first. You want them to come out first. If you want them to come out first, so that means you have to what? That means we can actually do something to reverse the charge on the capillary wall. How can we do that? We actually can add some surfactant. We can add some cationic surfactant. We can add some cationic surfactant. So they are those ones with alkyl ammonium salt. So they have a positive ammonium head, and then they have hydrophobic long alkyl carbon chain tail. So they have hydrophobic tail and hydrophilic charged, the positive charged head. Okay, so and what happens is like when you add this surfactant in, so those surfactant, so the positive head will pointing attracted to those negative charge on capillary wall, and then they have the long tail pointing outside because they add more surfactant. So the cationic surfactant, the long tail, will like say attracted or bind to the tail of the one that already attached to the negative charge, and then they form the cationic surfactant bilayer. So the net result of that is now, so all those negative charge, they have been masked, okay? They have been masked. And now you have a layer of what? You have a layer of positive charge is pointing outside, okay? So by this way, the ammonium head, okay, so they are now pointing towards the solution. So, and then, so they make the inner side wall of capillary to be pseudolily positively charged, okay? And then, so that makes the capillary surface become positively charged. And then now, so in the mobile phase, in the buffer solution, it will be the iodine. So now they're attracted to the fixed layer and to the mobile layer. And then will be the iodine. So in the mobile layer, they are pulling, they're attracted to the anode. So now the EOF, electro-osmotic flow, is going to the anode, okay? It's to that direction. And then, so you should put the detector here in the other direction. And then, okay, by this way, so then the negative ions will come out first, then neutral, and then positive ions. Understand? So this is how to change that. So by doing this way, this is how you do that. Now you get the detector now. So by what? The detector now, so by anode. So you just reverse that, and then so because we add the surfactant, we change the polarity of the inner wall, and also now so everything sweep to EOF, go to the anode instead of cathode. That's it. Okay. So, but we know that limitation. Limitation for this one is still doesn't matter. Neutral compound cannot be separated. So how can we solve that problem? So we can using the micellar electrochromatic capillary chromatography to solve that problem. So micellar, what is that? So that means inside. So it will call some micelle, okay? So it's MECC, okay? So, and what is the micelle? Micelle also is added formed by surfactant. So what kind of surfactant? So a normally one is sodium carbon 12. This one, SDS. You will often see that one. This is very commonly used surfactant. It's pretty cheap and it's very popular, high purity. So not expensive. So that's why I make it popular. So is this one? CH2. Total 12 carbon, okay? So that's why it's called Dodacil. Dodacil means 12, okay? And negative, positive, right? Okay, so this is the SDS, okay? So you can see that SDS, it has a C12 carbon tail. This is tail, right? Okay, and then so it has a sulfate head. So, and it has negative head, and it has hydrophobic tail, like that way. And then, so once, so, and the surfactant concentration, if it's at high enough concentration, if its concentration is higher than the critical micellar concentration, we call that CMC, the critical micellar concentration, CMC, and then it will form a micelle like this one. It forms micelle, so which has all the polar head pointing outside, and then it has the hydrophobic tail and pointing inside. And we can see that this one is now it has hydrophilic head, which is polar head, be hydrated, okay, and which has hydrophobic inner side. So this is hydrophobic because this has a lot of non-polar hydrophobic chain. Okay, interesting, right? Okay, but this compound now is negative charge. Okay, and have many negative charge, has large Q value, right? But at the same time, it has large size as well, right? Okay, so this is anionic, but also you can have the cationic one. Cationic one always normally just aiming that, right? Okay, and also it has triionic one or non-ionic surfactant. But there are different kinds of surfactants, and then they form the micelle. A micelle consists of the 40 to 100 surfactant molecules, just like squeezed together. And then, so this is how it looks in aqueous solution. So it looks like, so, and then, so it has, if we say that amphiphilic, because within this molecule, so it has, we have one hydrophilic head and hydrophobic tail, and this hydrophobic tail, and this hydrophilic tail, the head, okay? So, and we also mentioned only when the concentration is greater than CMC, and then for micelle. And for different kind of surfactant, so it requires different number of monomers to form this micelle. And also the temperature of system should be greater than the critical micellar So, and temperature. So if I look at that one, so, and it's more structure looking of that SDS micelle. So center, we keep saying center hydrophobic, center hydrophobic. There should be a reason why I keep saying that. Why I keep saying hydrophobic, hydrophobic for center, hydrophilic for head, charged outside. It should be a reason. Okay. So now let's look at the critical micelle concentration and the aggregation number of some commonly used surfactant. So, and for sure, SDS is most popular one. Also has sodium octyl sulfate. Okay, and you can see that for SDS, N number is 62, and the critical micellar concentration is 8.1 millimole. What does that mean 62? That means for each of the micelle of SDS contains 62 monomer. The answer is no. It's polydispersed, okay, the micelle. So, and it has kind of the variation of the number of the monomer get involved. And this number, N equals 62, is just average. It's just average, okay? So the N number actually has a variation. So, and cause, so, and relatively large range of the micelle cell size, and then also the charge to size ratio, and then make it has different mu EP, and then so cause that band dispersion broadening. Okay. So, and also this is example for cationic surfactant. Again, see ammonia as we expected. So hexane diethyl trimethyl ammonium. So this is a C16, right? Okay, so C16N, but also here has trimethyl. So it's quaternary amine. And then, so this is DTAB is often used. This is a C12 carbon chain. You can see that for different surfactants, their aggregation number is different. This one has 78 for CTAC and 50 for DTAB. Okay, and Twitter ionic one, so it's like that one. So it has both ammonium and sulfate. So in its group, Okay, and also has some non-ionic surfactant, Triton X100, this one. So this one, and also the biosalt. This one itself is the chiral one. It's a chiral one. So it's can form some helical that the structure like this one. Okay, so and the micelle formation is a dynamic process. As we say, N is average aggregation number. So it's informed the micelle cell, critical micelle concentration influenced by organic content, temperature, and buffer, and so on. Okay, it's polydispersed. Okay, so and this is something, but why the micelle can do the separation? Okay, so it's based on the separation is different. Okay, so it has separation mechanism is different, and forever anyway. So we'll talk about that in detail. So for micelle and analyte interaction, actually your analyte can interact with the micelle. Which part? So if it is inner part, if inside, associate interaction is between that hydrophobic column, so that means the compound is non-polar to moderately polar. Okay, so and then so that interaction is more hydrophobic interaction, okay, or induced dipole interaction. But if your compound is polar and the more association with the hydrophilic head outside, because the micelle has so many hydrophilic head pointing outside. So if your compound is polar, and then so as interactions, more dipole interactions. Okay, so and they'll see, we'll exactly see. So and how does that happen? This shows the schematic of the micellar electrolytic. So and that's so capillary chromatography. Okay, so we can see that. So now the micelle, they are negatively charged on surface. So and so can anyone tell me? So now for the micelle, So what is the direction of this mu EP, electrolytic mobility? It's towards anode or towards cathode? It's towards anode, right? Okay. So the micelle itself is moving, it's like say mu EP is towards what? Towards the anode. So, and then the whole mobile phase now is moving towards the cathode. Okay. So, and now your sample, your compound. So, and anyone can tell me, so do experiment. So the buffer solution and the micelle, so which one moves faster? The buffer solution or the micelle? Which one moves faster? We're talking about how fast they go to the end. Obviously, which one? The buffer solution. The buffer solution, right? Is EOF. Because micelle is compared with buffer solution, it's a slower moving micelle, right? It's a slow moving micelle. So when the sample is introduced into the system, now the compound can do something. It is that sample. If your sample is a little bit hydrophobic, it can what? It can partition into the hydrophobic inner cell of the micelle between the polar aqueous phase buffer solution. Understand that? So if your compound is quite hydrophobic, so it can completely incorporate it into the hydrophobic core of the micelle, and then, so that means it's completely solubilized by the micelle, and then so that means it's going to travel together with the micelle. Understand? Okay, and then so it will become out late, right? Okay, so if your compound is totally very polar, if your compound does not partition into the hydrophobic core of the micelle at all, so it's 100% dissolved in mobile phase. So travel together in mobile phase, it comes out of the column fattest. Understand? So for very polar one, no partition to micelle. So travel with the mobile phase, with the bulk phase, and then so it goes together with the EOF. Okay, if it's neutral compound, we're now talking about neutral compound. Neutral compound. Okay, so neutral compound. So if like your compound so have no interaction into the hydrophobic inside of the micelle, so it's very polar. It just dissolves into the in the mobile aqueous phase. It just like say travel together with the aqueous phase, the buffer solution at EOF. Okay, so however, if your compound so it's totally soluble, so in the micelle, and when does it come out? If it's totally soluble, it will travel together with micelle. But now what happened to micelle? It has a EOF. At the same time, it also has a pretty big EP. It's pulling it because it has negative charge, multiple negative charge, even it has big size, but still pulling it. Understand? Okay, so and then, so that means your compound will come out much later. So how about, so that means for one totally, so polar one, not soluble by the one, so it comes T0. And for the one that really, so non-polar dissolved in micelle, then comes out the time of micelle. And how about for other compounds? If the compound have intermediate polarity, it can distribute between micelle and aqueous phase, depends on its polarity. So, and your compound will come out between T0 and TMC. Understand? Understand now? Understand now, okay? So the separation of the neutral analytes is based on their partition between the aqueous buffer and the hydrophobic micelle core. So this is the separation mechanism. So of this MEKC. Understand now? Okay. So it really depends on the relative hydrophobicity of the compound. So depends on its partition between the hydrophobic cone of the micelle and also the polar aqueous buffer. Okay. If you look at this one, so when you inject your sample, and then so what comes out first? So your buffer. So buffer here, mu apparent equal to mu EOF. Okay. So and this one micelle, mu apparent equal mu EOF plus mu EP, but now the mu EP is negative. Okay, minus, then we can do that. How about if we say that, let's say that I minus that absolute value of mu EP. Can I do that? Okay, so minus that. So, and the analyte will migrate. So if in between, so that comes out, so in between, okay? So what we normally do is you have to know, so what is that T0? So because we can define that. It is often defined that the ratio, because everything comes out between TMC and T0. We define that the ratio of TMC, you'll see that in some book, just for information, over T0 is defined of elution ratio. And also the time between T0 and TMC, this one is called the migration window. Because this is how the neutral compound can be separated. So they are separated between T0. And then it's possible to measure T0 by adding a very hydrophilic compound, such as methanol here. And then because we have very so polar, so it would just dissolve that. So in the buffer solution, it would not partition into the hydrophobic micelle cone, so it will elute at T0. And then, so how to determine the micelle, this one, the end time for that one, so where that one comes out. And then, so you can normally add a hydrophobic compound, very hydrophobic compound. For example, the Sudan-di-3. Sudan-di-3 is completely soluble. For example, this is structure of Sudan-di-3. It's for your information. Here's information. So it's because they say, how can I know? How can I know it's the end of TMC? How do I know it's T0? This is how you do that. You have to use some indicator. You have to use some micellar marker, we call that, to tell you, here comes the micelle. And okay, so, and this is the C. Sudan-di-3. Okay, so this one can put an indicator, so for the micelle, because it's totally soluble. So it will be micellar. It's a micellar marker, and we call that methanol like EOF marker. And this will be micellar marker. Okay, so and then indicate the TMC and T0. And so this is that. So we can also call that, because now you are fast moving buffer solution, you have the slower moving micelle. So the micelle is serving as the pseudo stationary phase. So and then, so this one, the MKCC is the micellar electrokinetic capillary. So it's serving as what? It's serving as kind of the hybrid of traditional CE and reverse phase chromatography, right? Okay. So because the micellar are negative charge, they migrate towards the cathode with low velocity than that for cation. So neutral species will partition between the micellar and the buffer, similar to what we see in HPLC. For neutral compound to be separated, they must have some solubility in both micelle and solute. If not, so they dilute as some single band. That's it. Okay, so and there's different selectivity for that micellar structure. Definitely will influence that selectivity because you can choose different ionic group. You can already see anionic, cationic, triionic, right? So also they have difference in the distribution coefficient. I mean for the anions. So because the polarity, so hydrophobicity and so on. So that interaction is not really to the hydrophobic center. Sometimes if a polar compound, it can happen for outside as well. So and then so it's similarly, just like say how they can interact with the micellar and also so the running buffer solution. That's it. So sometimes mixed micellar with ionic and non-ionic surfactants can be used. If that is the case, then you see the charge is still that same charge. But if it adds some non-ionic surfactant to grow a much bigger micelle, and then so radius increase. And then so then it has lower charge density. And then so the electron ferrite mobility reduce, and then you have smaller TMC, and then you have the narrower migration window, right? That is the case for that one. For temperature, if you increase the temperature, and then so and that partition distribution coefficient decrease, and then the temperature, the time also decrease because more like say in travel together with a mobile phase, right? And then so also the both the electro-osmotic flow and also electrophoretic mobility increase because the viscosity decrease. Okay. So, and also pH is critical for ionizable analyte. So, and it influences the EOF, right? And also the, we also can add some additive or something like into the aqueous phase, for example. So, and for the chiral separation, if we want to separate, so the isomers, the chiral isomers of the neutral compound, we can add the cyclone, so dextrin CD, so into the mobile phase as well. And then so that will even achieve the separation of the neutral compound. So that's chiral neutral compounds, okay? So that is even more powerful. So, and that's it. So let's see the application. So you can see now, number 1, methanol, number 8, student 3. So this means T0, this is TMC. Okay, so you can see that they add the surfactant, 50 millimole, so SDS. So in 100 millimole of borate and 50 millimole phosphate, buffer pH 7, that is very common for the condition, and borate and phosphate. So they are also very common. So buffer solution used as well. So and you can see 65 centimeter long, 15 K volts, that one. So it somehow used 210 nanometer. So for that, for the measurement. So, and also this one, those like say, so yeah, with aromatic ring, So we can see that if we compare with that micelle and with that, so a reverse phase HPLC, we can see that. So micelle, that one has much higher so separation efficiency. So then reverse phase HPLC, however, so you normally just handle a small amount of sample, and so and this is disadvantage, and also for the advantage, so change the second phase in micelle is simple. So because now we have the pseudo stationary phase. The pseudo stationary phase is the hydrophobic cone of what? Hydrophobic cone of the surfactant of the micelle, right? Okay. So if we change the surfactant, you change the pseudo stationary phase. So, And in contrast, if you want to change stationary phase of the HPLC, you have to change the column. So, and disadvantage for that one, so the micelle is only applied for the separation of small molecules because the compound, especially those hydrophobic one, it has to partition into its micellar core. So that one, so that means, so it has some limitation about the size. It cannot be a very huge one. So, and however, the reverse phase HPLC can treat big molecules, so such as proteins. So now how about we talk about the chiral separation? Okay, so that is the last part. We go pretty fast. Okay, so it's also possible to separate the enantiomers using the C. What is enantiomers? So enantiomer is one of the two stereoisomers that are mirror image of each other, like our hands, left hand and right hand, right? Okay, so they are enantiomer. So, and the mirror image. So it's very challenging to separate them. So, and however, C can use for some chiral separation. The most common approach using CE to do the chiral separation is to add cyclodextrins, CDs. This one's already talked about the CDs into the buffer solution. So, and normally the concentration is 1 to 100 millimole. And then, so we can see that. So the cyclodextrin, so you can see they are just some modified compound. They are that those oligosaccharides. So oligosaccharides, just this one. This is single saccharide sugar compound. Actually, we call that polysaccharides. So and then so they just like say a number of them. So just like say combined together, so they form that cyclic one. So and you can even chemically modify this cyclodextrin. So for that, because outside you see that outside there are many of the OH group. So see that some of the OH group have been chemically modified, replace that hydroxy, so by R group. Okay, so it can be either dimethylated, so or hydroxyproponated. So and then that would be the beta cyclodextrin. And then the use of CD is especially effective for the separation of those so aromatic compounds. So the isomers of aromatics and also the aromatic enantiomers that have chiral center close to aromatic ring. So they'll be more effectively separated by CD, okay, by the application so of this one. So what happened is here. Now the CD is neutral. This one is not charged, okay? This one is neutral. So there's no charge. The CD is electrically neutral. So it is not kind of affected by EP, right? Okay. So that means CD itself. So just cannot be used as the carrier that one. So for the micellar, okay, because it's not CD itself, it does not have same as the micellar has negative charge or positive charge. So it's like migrating of itself. It's migrating together with the buffer solution, right? Okay, it's migrating buffer solution. So how about, so when it's introduced into the C, and then how can it achieve the chiral separation? Because it depends on the compound. For example, so if now the isomers or enantiomers you have, you can see DL, okay? It's positively charged. What happened? Because now we can see all the isomer D, so they cannot get into the CD because now it's chiral selector, okay? So only one enantiomer, so chiral isomer can get in, which is L form, not the D form, okay? So you can see that. So because the CD has the activity for the chiral separation, so one particular isomer get into the CD, and the other form left that so into so in a mobile phase. But of course, this one also can not 100% can diffuse in and out. Okay, so they're positively charged. So when they are positive charged, normally it's happen at, so if it's cationic, if positive charged, so normally it has at low pH, okay? If it's for this particular case, okay? For this particular case, because of positive charge, we say this is high chance is a low pH. Okay, it's positive charged. And then so what happened? So analyte protonated at the pH. And then so they actually have an electrophoretic mobility towards the detector, towards the cathode, right? Okay, but however, when it interacts with the CD, the size increase or decrease? The size increase, right? Okay, and now what happened? When the size increase, so electron, its original mu EP will decrease because the size increase is Q over R decrease, right? For this one, okay? And then so it's mu EP decrease. So, and then that's why compare with the AD, the one not really get into the CD, the chiral selector, and then so it travels slowly than the other. And then so the one did not get in, elute out first. And then so the one that can chirally selected by CD comes out later. It tends to migrate, so slower for this cationic enantiomer. So question, so how about for those negatively charged enantiomer? How about for those negatively charged enantiomer? What happened? Let's say a high pH. Now you're not, now you have say enantiomer AD minus, AL minus. So what happened? If the AL minus is 1, so that can get into the CD. What happened? Then which one comes out first? The AD minus or the AI minus, AL minus? Which one comes out first? Which one? Which one? And then so the one with CD, right? Because now it has larger size. The smaller mu EP, now the mu EP is pulling that. So less pulling, so that's why it comes out first. So this is how the chiral suppression achieved. Okay, so but then the question is like, how about for neutral compound? How about for the neutral chiral compound? They have no charge, and then so the CD has no charge. Okay, and then they cannot be separated. So how can that be? If I'm not separating any of the charged chiral compounds, I'm separating those neutral chiral species. How can I do? How can I do? So then this one, you have to use the CD modified. So micellar, so that's MEKC, okay? So, and electrokinetic capillary, okay? So, and this is what's showing here. So now you still have the micellar here, and then this is your CD. How about the chiral selector? This is chiral selector, which is neutral. And then, so this is your compound. You can see that you have compound. So those compound, so they can partition into the hydrophobic center, and only certain ones, so the enantiomers on this shape can get into the CD. Okay, so now we assume, and we assume that CD itself is not incorporating into the micelle because the surface of the CD is hydrophilic. This one, because the surface of CD is hydrophilic, so the CD is not getting into the hydrophobic form of the micelle. Okay, so the CD no, so it's just like a cell that dissolve in the water. So in the system, the CD migrates at the same velocity as what? EOF again. So this one only has EOF for CD. Okay, so and how about for micelle? We already know that micelle is acting as a pseudo-stationary phase. So it's migrating at much slower velocity, so than the EOF, right? Okay, so therefore the analyte, which is this one, which is the black one, the analyte which incorporates into the ionic micelle, so and oh no, this is this one is covered into the CD. So that means that this one, So this analytes that incorporate into the micelle, this one. So then they will travel at different velocity from the EOF, right? Okay, so in the case of those highly hydrophobic analytes, so they seem to be totally incorporated micelle and in the absence of CD. So, and therefore, if we kind of like, in addition, we add CD and then so the change, because now one of the enantiomer now prefer to be in the CD. And then can you tell me which one comes out first? A, B. Now you have two enantiomer. So, and B as a one, so that incorporate into the hydrophobic core of the micelle, and A as the one, so that selectively picked by this chiral selector. So, and can you tell me, so which one comes out first? Now the separation happened, because now it's distribution between micelle pseudostationary phase, CD aqueous phase, okay? And micelle negative charged, they have slower mobility, okay? So apparent mobility, and the CD now is neutral, it's moving together with the buffer solution, okay? Thank you very much. So now still answer my question so late. Then A comes up faster, right? A comes up first because now it's in CD, which is the neutral one species, which just come together, goes out together with EOF. Okay, and B now is in a micelle, and then so which comes out later. So this is how the separation of the neutral chiral species so get separated. Okay, so I hope, like say, I explained it clearly. So you can see that we have a lot of application of CE. There's very broad range of application to separate the biomolecules, the pollutants, and the chiral components. So you can so on. Okay, so and summary for that, you just remember the principle of the theory, and then so you should understand what's the factor, what is EOF, what is the EP, so what are the factors influence EOF and EP, so and also the mode of instrument. Okay, so so that's all. Okay, so that's all for today, and let me see. Be quickly. Okay. So do you guys have? Let me see. Let me share one. Let me see. Okay. So we actually have gone through many things, and the final exam will be just on my part. So I have also questions coming from the students. Probably I just took advantage to answer the question all together. So, and we talk about the N plate number. N is proportional to 1/dp. Okay, so they are L over dp. So this one is don't need to really worry about what the really meaning of reduced height equivalent to a theoretical plate. No, it's not, because that we already know that. So N equal to L over H, right? Okay, so and that one is the length, the plate height, and then it's really, and also it's proportional to 1/dp, and then you just relate the H, the total. Oops. So here, it just relate the plate height so with the dp, and then so it's kind of like gets a parameter in front of dp, so no need to worry about too much about that. Okay, so and this one, and also I have another question, so that is, let me see, oops, and so I have this one. So and student also asked about, so we do some comparison of this one. We talk about all these things. If we change the particle diameter packing material. So we keep saying like we change the dp, so particle diameter from 5 to 1.735 to 1.7. So if it decreased by 2 times, decreased by 3 times, how does that influence the speed and everything? So we did a lot of practice here. So see like if we keep the n unchanged resolution same, and how does that work? And if we keep the L the same, so how does that influence? Okay, so the reason for me to have this one is just want you guys understand how particle diameter influence the performance, okay? Influence the separation time, influence the speed, influence the resolution, influence the sensitivity, understand? Okay, so and we talk about in 2 different ways. We say like, if we want to achieve the best resolution, okay, and then so you change L, and then so obviously we can see then you have to face a very high pressure drop. So and however, so if your instrument you don't even want to handle that, so high pressure drop, and then so and you sacrifice you're okay with the resolution, and then then what is that case? So that is the point about so how we explain that. So what is the condition at constant column length? What is the condition at constant column efficiency? So you see that actually in reality, what we do is like say you don't want to really handle a very high pressure drop, and then normally we use smaller column for UPLC than HPLC, right? Okay, but it really depends on if you really like say your goal is like say you have very difficulty to do a very good separation, and then so you may want to pick the column so with even better resolution. Okay, so and also for some of the forms like that one, so no need to really say dig into the detail about how that derived, how that gets. Okay, so it's just for information. So you just know that. That's it. Okay, so well, I think that's all for what we have. And let me think. Probably I quickly go through. Like for UPLC, you guys already know the key points, right? So we go through everything together. So and the key point is you really have to know. So how does that influence? I will put, oops, right, I moved that one. Okay, so I will put, why cannot? I will put a star here. I guess like from here, you should really know. So then when DP change, so as I mentioned, so how that influenced L and how that influenced all the speed, resolution, and so DP and everything. Okay, so this is something like you definitely need to know. Okay, so and basically that's the key point here. So we spend a lot of time talking about that. Okay, so and let me see. For I try to go through one by one. Stop share, and then so 1 minute. Oh, so HPLC. And for HPLC, and we talk about the thin layer chromatography at the very beginning, right? Okay, so also I hope you guys understand. So the meaning of that thin layer chromatography, why we can use it, give us some screening, give us some preliminary idea about the retention, about the separation condition in the column chromatography. Okay, so how we get that value for that K prime, and then we come to, oops, so that one. So this one, we come to the LC part. So that means, I think here we get something about, yeah, I think some basic idea about the difference between HPLC and GC, and then if you get a compound, so which chromatography you need to choose for the separation. Okay, what is the criteria? So, and that's something you should know. And also then we talk about some instrumentations, but that one I say will they will go together with some real case. Okay, so because then later on we using size solution chromatography, that use ELSD, and then later on we talk about, like say, the several case studies talking about the metacount grain, also talking about so the melamine, then use mass spectrometer, right? Okay, so the detector we do not really separate talking about that, so they go together. So with the real application, okay. So, and also we talk about the 6-port injection. So that's something you should know. And let me see. And yeah, detector. Yeah, detector go together. Yeah. And then, so we really spent time about the column efficiency. So what are the parameters influence A, B, C? Okay. What is eddy diffusion? What is longitudinal diffusion? What is the non-equilibrium mass transfer? I hope you understand the meaning. Okay, and it's particularly for HPLC. I think, like say in first part when talking about GC, and Dr. Wang already talked about, so that the Van Diemen's equation and what is the ABC term, so that matter in GC. But here we also mentioned that, okay. But here I want you to know, like for HPLC, so which term matters and why is that, okay? So the meaning behind, okay. So and that is the one. So you're not really supposed to remember all this equation. No. Don't worry about that. But you should at least should know, like say, so the A term, this one is eddy diffusion. It's proportional to dP. It's related to particle diameter, right? And also you should know the B term. So longitudinal diffusion is really related to diffusion coefficient. But this is not the very critical term. So in LC. Okay, so why is that? And also you know the so the mass non-equilibrium of mass transfer, that C term does matter in HPLC from the moving mobile phase, stacked mobile phase, so on, and then so how is that related to the DP as well, right? Okay, so I think from that we really talk about. I hope you guys understand the meaning, and then that is connected to UPLC as well. Okay. So, and then we talk about the different application. So let me see. We talk about absorption and partition chromatography, and the focus definitely partition chromatography. Okay, so absorption chromatography we don't really spend much time. So focus on partition chromatography. From partition chromatography, okay, so this is common sense thing. So that is basic thing. So the how we can modify K, how we can modify alpha, right? So what is solvent selectivity? What is solvent selection? So if we want to achieve better separation, how we play with the solvent polarity index, how the solvent polarity index influence the K value. Okay, so we did that question together. So, and again, I hope this one, everybody knows how to do that. Okay, so, and we actually try another example as well. So, and just go through what we have learned. And then, so we talk about so how we can use in the solvent selective triangle to do that. So, but this is a very simple case. This is isocratic, but it's just giving us some idea about, so what is solvent selective triangle? And then, so what is the common solvent used in reverse phase chromatography? And what is that in normal phase separation? And then, of course, the focus will be more on reverse phase chromatography and this kind of thing. And then, so, and here we actually later on, we use 2 examples to go through. So, and I think the purpose of doing so, I already explained that to you guys, is I want you guys later on, when you are facing a real challenging or problem in doing your work, so what you're going to see is you only will know so what kind of compound you are analyzing, or sometimes you even don't know the clear structure of your compound. You just know what kind of group of compound they are, and based on their structure, based on the formula, So based on their chemical property, you should be able to understand or propose the right extraction method, okay, or even some sample cleanup method, okay, based on the structure. And then so you need to be able to propose a right column or right mobile phase condition for the separation analysis. And then the detector. If it's mass detector, we already talk about, like sample cleanup we talk about, right? Okay. And it's from mass detector, so mass spectrometer, is that one ESI positive or negative? Okay. So if it's you're using fluorescence or UV, so why you think you can achieve that enough sensitivity, right? Okay. So that is the point. Like say, probably I will give you just one or two compounds. You look at the structure, and then I told you what I'm expecting, and you're supposed to suggest and propose a procedure starting from the sample extraction to clean up to the LC, the liquid chromatography separation, and also detection. Okay, so and using those as example. Okay, so this is give you already pretty good example. And then we talk about another kind of the partition, and it's hydrophilic interaction liquid chromatography. What is a helix? Why helix can work for polar compound? Okay, so what is a typical application for helix? So this one, so how does that work? This one you're supposed to know. Okay, and also we give you one example of like say analyzing melamine in food using a helix, and that is another real practice we go together. Okay, with analyzing from structure, and then so starting from that extraction, cleanup, and analysis, right? Okay, especially all these kinds of practice here. So I already told you so why I do this, why I want you to think about it. Okay, so and that's for that part. And then so that is for ion chromatography. Okay, so for ion chromatography, and then so we'll definitely focus on exchange chromatography, but we also talk about the theory and principle of exclusion chromatography, of ion pairing chromatography. You have to know the working principle of all three. Okay, working principle. But talking about more details, applications, we'll focus on ion exchange chromatography. Okay, so ion exchange chromatography you should know is cation and ionine, and we have polymer-based matrix or silica-based matrix. Why? So polymer-based matrix more popular. And what is the limitation for the silica-based matrix? Okay, and then so and what influence that? So selectivity and capacity. So we talk about that. What influence selectivity and capacity, and especially we talk about affinity of the ions to the stationary phase. So and not just the charge density, also for the polarizability, right? Okay, so and give you extra ones to talk about that one. So and for cation, and also we mentioned about the suppressed conductivity. So as and some of the common mobile phase for cation and ionine chromatography, you have to know this is very, very common. And we talk about that here. For ionine, so sodium carbonate, bicarbonate, or sodium hydroxide. So, and what is the advantage and limitation for each of that eluent? Okay, and how that influence. But for cation, so if we want to separate alkaline metal, or if you want to separate both alkaline metal and alkaline earth metal, so what is the difference? And then so and how other parameters influence the separation. And for ion suppressed, what is the mechanism of chemical suppression? So how does it work for cation? How does it work for ion exchanger? So why? How it can reduce the noise background, how it can increase the signal, analyze signal. Okay, so that is very basic. Okay, so something you know, and pretty much that's all for ion chromatography, right? Okay, and last one. for the size illusion chromatography. For size illusion chromatography, we see that. So, and this one is different from all the other liquid chromatography. It's based on size. It does not want any interactions between the analyte and stationary phase, right? Okay, so, and we say that according to the polarity or solubility of the analyte, it can be the gel filtration or gel permeation. Okay, you have to know which one for which, right? Okay, and we focus on that gel permeation one because, so this one have some idea, okay? So because we talk about the application of the gel permeation one for the size, molecular weight distribution determination, right? Okay, and there's something about the mobile phase and stationary phase or size chromatography. They have some basic requirement, okay? So why is that? Okay, and for this one, so and for the size chromatography, so size formation chromatography, when we use that for the calibration for the molecular weight distribution, so determination. So how can we do the calibration? So what is that? And then and what is the criteria of doing so? And then so are we really like measuring the molecular weight or molecular size? So how does that relate to molecular weight, right? Okay, so and a little bit detail about sample preparation and also the detector. So that's it, okay? So basically that's all, and this is summary, something you just read through. And then so basically that's all for that. We have a lot of content. So and the examination will be online. So and after that will be the CE. So if you have, let me see, I think we had some take-home examination maybe 2 years ago. Probably I'm going to upload that onto the BU e-learning. So the previous take-home exam paper, and then you can read that and you have some idea. Don't send me email, ask me to provide you answer. Okay, so this question I'm supposed to do that independently, and also if you want to practice, and you can find answer from the notes and from the what I teach you, so explain to you in class. Don't directly send answer. What is answer for that? What is answer for that? And I do this correct or not? So try that by yourself, okay? So if you really have difficulty, that's another story. Well, anyway, so and for next week, we're going to have the oral presentation. So I'm going to upload the marking sheet on the BU e-learning, and you're supposed to give marks to your classmates as well. Okay, and remember rehearsal. Do rehearsal before you give the orientation, and very precisely control your time. Control your time. Okay, and then so do rehearsal, and that is very important. Okay, so that's all for today. So sorry guys for holding you along, because I really want to explain the things about what we're going to cover. So and that's all. So bye everyone. So we can just like leave now. Okay, bye. So see you next week. Remember to email me. Okay, the copy. Okay, so before you do the oral presentation, remember to check the guideline oral presentation. See the requirement of time, see what you need to send to me, and see what you need to reply to me. Okay, so that's it. See you next week. So I'm going to also, you guys join see Dr. Wang as well. So bye.